Hi everyone, and welcome to another seminar of Physics Latam. Today we are very happy to have Kasia Rejzner to give an introduction to algebraic quantum field theory. She's a Polish mathematical physicist specializing in algebraic quantum field theory and the theory of renormalization, including the Batali-Bielsko-Binsky formalism. She works as a professor in the mathematics department at the University of York. In 2016 and 2017, she visited Perimeter Institute as the Eminother Visiting Fellow. She is the author of the book Perturbative Algebraic Quantum Field Theory, an introduction for mathematicians. This year until 2026, she serves as the president of the International Association of Mathematical Physics, being the first female in these positions since the foundation project. Congratulations on that. Remember to raise the hand if you have any question, and I will leave you with Kasia. Please go ahead.
Thank you. Thank you very much for this nice introduction and for inviting me to give a lecture here. So this will start for sure as a very standard introduction to AQFT, and then let's see if we get to the perturbative story. So I'm going to mostly follow the lecture notes that you can find online. These are the lecture notes I wrote together with my colleague Chris Fuster, and they're essentially sort of gentle introduction into AQFT. So before we start talking about quantum field theory, it's worth kind of reviewing what you know about quantum mechanics in the algebraic approach. So before we go anywhere near QFT, let's start with algebraic quantum mechanics. Okay, so the main difference between this approach and what you might be more familiar with, like with Schrödinger's equation, is that it has more emphasis on observables, on operators, and somehow less on Hilbert spaces. So as a primary object, we consider some algebra of operators that models observables. So the first postulate is that a system is described by some unital star algebra. I will explain these notions in a second. Algebra A, and self-adjoint elements there will correspond to observables. So observable. So this is a sort of connection to physics. Okay. And very often, well, so this is the basic is this unital C star algebra, sorry, unital star algebra, but very often we also assume something stronger, that A is C star. So often A to be C star algebra. Okay, so let me define some of these notions in case you're not super familiar with this. So the first definition, what's a star algebra? So star algebra A, well, first of all, is an algebra, and I will always work over complex numbers. An algebra over C. And we have the star operation called an involution. So with a map star going from A to A called involution. Okay. And this map satisfies the following. So first, for all A, B in A, we have some sort of linearity happening here. So this is a linear operation. And if we look at the product, then it kind of switches positions in the product. Okay, and then if we multiply things, this is also kind of compatible with this operation. So if we have a complex number and an element of the algebra, then we want lambda A involution to be the complex conjugation of that times involution of A. And finally, like if we take this operation twice, then we are back to the starting point. So A star star is the same as A. So this is an involution. Now, unital, it means that we have an element called a unit. So another definition, there will be a number of those at the beginning before we can get started with examples. So a star algebra is unital if it has an element that I will denote like this, sort of flattened one. Well, first of all, it's a unit for the product, which is a unit for the product. And in addition, has nice properties with respect to the involution. So, and is invariant under star. Okay. So that defines both words at the very beginning. And now I'm left with telling you what's a C-star algebra. So before we get there, well, let's look at an example of, well, sort of motivation for that story, namely the algebra of bounded operators in a Hilbert space. So here, note. So for a Hilbert space, H, so B of H, bounded operators, is a star algebra. Okay, and the star operation is the notion of the adjoint. So a star is the adjoint of A. Okay, so if you want to recall the notion of the adjoint, we have two vector state. We have A acting on one. We have the product of the Hilbert space. So adjoint is the element that satisfies this. So we bring it over to the other side of the product. Okay, so that's the sort of running example. So yeah, so that I guess covers maybe the observable side modulo the C-star story that I'm going to explain in a minute. Now, what about states? So I kind of mentioned Hilbert spaces, but here, as I said, the states are slightly less prominent. So here, the second postulate of algebraic quantum mechanics concerns states. And these are functionals on these operators, on the observables. So are positive normalized functionals. So omega going from A to C, and then positive. What does it mean? It means that omega of A star A, so of a positive element, is greater or equal 0. And normalized, it means that if omega acts on our unit, then it gives 1. Okay, and being functionals, well, it means that they're linear. So linear. Okay, and there is well, definition of pure and mixed, which very often comes up in quantum mechanics. So a state is mixed if it is a convex combination of distinct states omega 1, omega 2. So omega is some lambda omega 1 plus 1 minus lambda omega 2, where lambda is between 0 and 1, and distinct, so omega 1 is not equal omega 2. So that's mixed, and if it's not mixed, then it's pure. So if you cannot decompose it this way, then it's called pure. So otherwise, the state is pure. Okay. So these are the basic definitions. So what else do we need for our algebra of observables? Well, this was all very algebraic in a sense. I defined those operations, but sometimes we also need notions of convergence. We want to be able to approximate some elements by other elements, by sequences of other elements. So it's useful to have some topology on this algebra A. And well, nice topologies arise from a norm. So it's useful to assume that we have a norm on our algebra. So again, one more definition, a normed algebra A is, well, algebra equipped with a norm such that, so this is compatibility between the norm and the product of the algebra. So the norm of A times B is less than equal norm of A times norm of B. Okay, and then if it is unital, so if unital, then we require that, well, the norm of the unit is 1, so that's also kind of logical. Okay, and then another good thing we can ask is some sort of completeness, so that if we take sequences in this algebra which behave nicely with respect to the norm, so they look like they are converging, we call that Cauchy sequences. So they look like they are converging, they're getting, the terms are getting closer and closer to each other, and we want that to actually indicate that the series converges within that given space. So such a space is called complete. So this norm here defines as the notion of convergence. So we can ask whether our algebra is complete with respect to that norm. So,
Hello.
yes?
Ma'am, I had a question. So,
Yeah.
here you defined the mixed states like lambda omega 1 plus 1 minus lambda omega 2. So, does this also include the notion of like entangled states as well, in which the states are not decomposable? Like, does this
Yeah,
definition?
so this is a very sort of general definition. So here, yeah, I'm not really assuming anything about where that state comes from. and how I construct it. So it's just any functional on my algebra. And then I ask the question if I can decompose it or not. So if I can decompose it, then it is mixed. If I cannot decompose it, then it is pure. So this notion of states is well, somewhat more general than, say, vector states or even states that arise from density matrices. So this is just what it is, if that makes sense. But it applies also to states that you cannot like easily construct from density matrices or vectors.
Okay, thank you.
Okay, thank you for the question. Okay, so yeah, so the completeness, so if A is complete in the norm topology, then we call it a Banach algebra. Okay, so this is something quite useful to have. And finally, let's come to, okay, so let's see also what it does with the involution. So if, oops, if A has involution, then we require that the norm of A star is equal to the norm of A. So then we have a Banach star algebra. And finally, the C star algebra at the end of the very long story. So A is a C star algebra if it is a Banach star algebra as above, and has something called a C star property, namely the norm of A star A is the norm of A squared for all A in A. So this is C star property. Okay, so you might have heard here or there that in algebraic quantum field theory, we talk about nets of C star algebras. So it's good to know what this actually means, where this comes from. And here, coming back to our favorite examples, some bounded operators on a Hilbert space, they actually do form a C star algebra. So note, so B of H is a C star algebra. So it's a good running example. Okay, and then let me show a couple of examples of how to get states. And this is, well, somewhat related to the previous question. So let A be this B of H. And, well, it's reasonable to assume that the unit coincides with the identity map on H. So with the natural notion of the unit. So then every unit vector psi in H defines a state. Let's call it omega psi of A, which is given by this expectation value. So this is a sort of simple example of how a vector in a Hilbert space gives us a state in this more general sense. So you can check, right? So I said, what did I say here? You can check the definition. I say that we have to have positivity and normalization. So let's check it quickly for this obvious example coming from a unit vector. So normalization. Okay, so omega psi acting on the unit. Well, that's psi unit acting on psi, which I said is the identity. So it's just psi product psi, and I said it was a unit vector, so this is 1. Okay, so we have that. And the other was positivity. So we have omega psi of A star A, and this is just psi A star A psi. We can use the definition of the adjoint to bring A star to the other side. So we have A psi A psi. So this is just the norm of this vector A psi squared, which is obviously greater or equal 0. So this indeed defines us a state in this more general algebraic setting. And another example is given by density matrix. So take rho a positive trace class operator on H, so also known as density matrix. Positive with, okay, with, let me write it here, with trace rho equals 1. And this defines a state. So define a state omega rho of A is the trace of rho times A. So this defines a large class of states. But as I said, not all states arise in these natural ways. So there are more algebraic states than just that. Okay, so these are the sort of basic ingredients. We are still in the quantum mechanics context. And already in this context, well, we want to make a connection between, well, what you know from quantum mechanics in this Schrödinger picture and this more algebraic approach. So the first step is, well, to introduce the notion of representation. So the way we kind of connect to Hilbert spaces right now is by representing your abstract algebra of operators, which is, say, star algebra or C-star algebra, representing it by concrete operators on a Hilbert space. So this is the first kind of link. So definition, a representation. And I'm going to work here with general unitar star algebras, so not assuming C-star. This is also motivated if I want to go to perturbative AQFT, I'm still going to work with unital star algebras, but no longer C-star. So this definition, some of the results that I'm going to give you right now, they generalize also to the perturbative setting. So a representation of a unital star algebra A, that's very, okay. A is a triple. So there is a Hilbert space, there is a dense domain, and there is a map pi. So Hilbert space. This is a dense subspace. And pi is a map from A to operators, not necessarily bounded on H. Okay, so it's a triple such that, okay, and what do we want? Well, first of all, yeah, so this story with the domain here, this is motivated by the fact that not all the operators are bounded. So bounded operators are defined on all of Hilbert space. Unbounded operators are only defined on a dense domain. Don't know if you have studied that in detail, but like even very harmless position and momentum operators on the line. So if you're just looking at a particle on the line, these operators are unbounded. So you have to, well, be able to understand such operators. And for that, you need to always specify a domain on which they are defined. So even if sometimes in physics you don't really worry about that because it's quite obvious what to do, it's good to have that in mind. So first of all, okay, so each pi of A has domain D of A contained, sorry, D of pi of A, which is equal to that common dense domain D, and range, so the image contained in this D. So I just need to, okay, something that should work now. Then if we represent the identity, this should be just the identity, sorry, the unit when restricted to D. And pi, well, as representations should, is linear and respects products. Is linear and respects products. Okay, and then finally, again, coming back to the domain issues, we have the star operation. So we want to be able to take adjoints in the representation. And we want some sort of compatibility there as well. So each pi of A has an adjoint, okay, in the Hilbert space sense with such that this curly D is in the domain of this adjoint. And it's the restriction which is defined this way, obeys the following. So if we take this adjoint of pi of A restricted to D, this is the same as taking the representation of A star. So this is the compatibility between, so on this side we have Hilbert space adjoint. So as operators on H, and here we have star operation in the algebra. So involution in A. Okay, so this is how given an algebra in this abstract sense, we get something concrete as operators acting on a Hilbert space. And then another important notion is, okay, I mean, there are many different representations, and well, what kind of specifies a nice representation. So very often we want this representation to be faithful. So pi is faithful if kernel of pi is trivial. Okay, so we we don't want it to like forget information about what's happening in the algebra. If there are some non-trivial relations there, we don't want to kill them. We don't want to put them to zero. And another important notion is irreducible. Irreducible. And this is somewhat more abstract. So it says that in my Hilbert space, there is, so the only subspaces in that Hilbert space which are invariant under all of the operators represented from A are trivial or dense in H, so essentially all of H. So if the only subspaces of H invariant under all of pi of A are trivial or dense in H. So faithful representation, irreducible representation. Okay, so finally, let me state the sort of most important theorem that links the algebraic formulation to the Hilbert space formulation, and you might have heard of it before. It's called GNS, so Gelfand, Naimark, and Siegel. So it always comes at the beginning of AQFT lecture, GNS theorem. What you might not have seen before is the formulation for star algebras. Usually people give it for C-star algebras, but if you want to, again, think about perturbative formulation, then you want this more general version. So I'm going to give it to you right now. So this shows how, given a state, algebraic state, you get a Hilbert space representation and you can connect to things you know. So let omega be a state, algebraic state on unital C-star algebra A. Then there is a representation coming from that state, H omega d omega I omega of A and a unit vector omega, oh, sorry, it's unfortunate, omega subscript omega in this dense domain such that, well, first of all, this domain is equal to pi omega of all of A acting on this. So you can generate that whole domain by acting with elements from the algebra on that vector state. And there is a formula, omega of A can be written as the expectation value for this vector state for all A in A. Okay, now another part of this theorem. So this tells us that a representation exists. Now the question is, how unique is such representation? Is there more than one? Is there just one? Are there many? So it turns out that this is actually unique up to an equivalence, which is a very natural notion of equivalence, namely unitary equivalence. So furthermore, this representation is unique up to unitary equivalence. Okay, this is also good to know. And let me state the definition of the unitary equivalence if you don't know it. Okay, so I have two representations, H1, D1, I1, and H2, D2, I2 are unitarily equivalent if there exists a unitary map U going from one Hilbert space to the other. Okay, so then we have to look at the domains. So this should restrict to an isomorphism of these domains. So isomorphism between D1 and D2. And this U is supposed to intertwine between these representations. So U acting on pi1 of A is the same as pi2 of A acting on U. So this is the intertwining property for that unitary. Okay, and obviously, if two representations are not unitarily equivalent, and they are unitarily inequivalent, which is also an important notion in quantum field theory. So in the sense, one can think of this equivalence as a very natural equivalence of representations. So unitarily equivalent representations are, well, somewhat very close to each other. There is a way to bring things from one to the other at just using a unitary map. So it's a very natural notion of saying that these representations are equivalent. Okay, so coming back to the plot, right? So sorry, coming back to the plot, for every algebraic state, there exists such representation, which is unitary. Well, it's unique up to unitary equivalence, which is great. So let me just say a few words about the proof of the GNS theorem. So if you want to see the whole proof, you can look at the notes in the reference I gave you. But let me just tell you the main idea. So the main idea is that you construct your Hilbert space out of the elements of your algebra. So you want to construct your So construct your Hilbert space H omega from the elements of A. Okay, so well, A is already a vector space, which is great. So what we need for a Hilbert space would be an inner product. So let's postulate an inner product. So define the inner product so A, B are elements of A, and we define the inner product of A with B as omega of A star B. Okay, so we can always do that. And then we will need a few things about that product that can be proven, and this is essentially the content of the proof of the GNS theorem. So the product, if we define it like that, actually it's not too great because it can be degenerate. So there could be non-trivial elements of A such that this product vanishes. So note, we could have elements with a product A is A star A, which is 0 for non-trivial A. So we essentially need to quotient out such elements. So these turns out form an ideal, and we quotient them out. So in fact, H is really defined by equivalence classes. So obtain equivalence classes. A, B. And then you want to show that it's a Hilbert space, what you obtain, and that these properties above hold. So I'm not going to I'm not going to go through that in detail. You can have a look at the notes I recommended at the beginning. Go through the details of the proof and get a better idea of what's going on. Okay, so that was the part of many definitions. This, as I said, this whole framework works for now in quantum mechanics. Now I haven't told you what makes quantum field theory here. So now we take this point of view that operators, observables can be for Hilbert spaces, and then we want to bring it to the QFT context. So what we need in that mix is the notion of causality. So that finishes quantum mechanics. So let's now talk about QFT. So what's QFT? Well, this is quantum mechanics plus special relativity. So from quantum mechanics, we want to take our observables and states. So observables are here elements of this abstract star algebra, and states functionals on A. Now, what do we want from special relativity? We want some notion of causality. So this is what distinguishes quantum field theory from quantum mechanics, is that somehow we want causality in the game, and this is sort of reflecting the principle that nothing travels faster than light. Okay, so this is the principle we want to implement. So yeah, in practice, algebraic quantum field theory is an approach which allows to do that. So yeah, I don't know how much people are familiar with sort of basic special relativity, but I assume that this is covered in a standard physics course. So let's start with Minkowski spacetime. And let's do it in 4 dimensions. So this is R4 with the metric, which I'm going to fix this signature just for concreteness, but it doesn't really matter in the end. You can write it in any signature, but then you have to translate the signs to do what you want. So this is Minkowski spacetime. So in Minkowski spacetime, well, let's draw maybe a 2-dimensional example. So if we look at just 2 dimensions, we have space, we have time, and then, well, this nothing travels faster than light is reflected in the fact that we can draw the light cone. Let's assume that the speed of light is equal to 1 in appropriate units. This light cone kind of separates the regions which are space-like. So these are outside the light cone, well, from the origin. Okay. Regions which are in the future of the origin. So it's inside the light cone, but for positive time. And things that are in the past. So intuitively, things from the past can affect what happens here at the origin, and what happens here at the origin affects the future. Things that are space-like are completely dependent, so they cannot really know anything about what's going on here. So they are elsewhere. So the idea of quantum field theory in the algebraic approach is to define physics in terms of assigning algebra of observables to regions of spacetime. So here is a schematic of the spacetime, and we want to take regions O in M, which are bounded, and we want to localize observables in those regions. So we want to assign to this an algebra A of O, which we assume to be a unital star algebra. And this is interpreted as observables localized in O. Okay, and then, well, what sort of algebra that is? We will also assume that this can be embedded in some sort of global algebra, which is also a unital star algebra, which in AQFT literature is called the quasi-local algebra. And in some sense, this quasi-local algebra is generated by these little guys. Another maybe remark here. So these are, well, any bounded regions, but we want actually to assume something more. So if we have a region okay? And we have 2 points, x, y there, and we have a causal curve connecting them. So it's time-like or null. Okay, so we want that curve to stay within this region. We don't want the region to be such that the causal curve gets out. So if a region contains all the causal curves starting and finishing, inside it, then we call such region causally convex. Then we call it causally convex. So this is somewhat well related to a compatibility with the causality. So let's assume our regions for the definition of QFT to be also causally convex. So bounded regions that are causally convex. And a nice example of such region is the causal diamond. So the causal diamond, we take a ball in the spatial direction and then take its causal completion, and then we get this. So this is causal diamond. These are favorite regions of AQFT. Okay, so we are localizing those algebras in regions. And then so the first, let's upgrade it to an axiom. So this is the first axiom, that we assign algebras to regions. The second axiom, well, so what happens if we have larger regions? So if I have O1 and O2, so O1 contained in O2, then we want A of O1 to be contained in A of O2. So this is the notion of subsystems. And this is called isotony axiom. Okay, then another axiom. This is finally going back to this special relativity principle, nothing travels faster than light. So if I take two regions, O1, O2, which are space-like separated, okay, then I want this algebras to be independent. So then I want A of O1 to commute with A of O2. So this is 0. So this is Einstein causality. And then finally, two more. Okay, so the second one is very special to Minkowski spacetime. Up to now, we haven't really used the fact that we're on Minkowski. This could be true in any curved spacetime. Now, the next axiom has something to do with the symmetry group of Minkowski. So let P0 be the identity connected component of the Poincare group, which is the isometry group of Minkowski. Okay. Then for each element, so for each row in P0, we have an automorphism . alpha of rho of this quasi-local algebra A of M such that alpha of rho takes the local algebra of O to the local algebra of transformed O. Okay, so think about a simple example of a translation. So we have O, we have some, oops, let's make it the same-ish. So this is rho, so we move elsewhere. And then this is A of O, and that goes under alpha 2. I should make this more prominent. Okay, and this goes to alpha rho of A of O. Okay, so that is called Poincare covariance. Okay, and it's very special to Minkowski spacetime because of the presence of the symmetry group there. And finally, there is something called the time slice axiom, which has something to do with the existence of dynamics. So let me draw this picture. So let's say that we have a diamond and we have a Cauchy surface sigma and some neighborhood of that Cauchy surface that, oops, that I call N. Oh, that's not good. Okay, and then we know that the algebra A of N is contained in A of O because of the isotony, but the time slice axiom states that essentially all the information is already contained in the neighborhood of a Cauchy surface, the same as, well, in classical field theory, given positions and momenta, well, the derivatives of your fields in the vicinity of a Cauchy surface, you can reconstruct the solution. So here in such situation, you have A of N is actually equal to A of O. So you have exactly the same information in the small neighborhood in the slice, time slice around Cauchy surface as you have in this whole region. Okay, so that there is slightly more than that. If you look into the book of Rudolf Haag, you will find there are more things about various properties of the vacuum representation, vacuum state that kind of fall into that package of axioms. But well, let's stop for now with this definition of what an AQFT is. It's a natural moment to take a break, and after the break, I will give you some examples and discuss some, well, if we have time, some properties of those local algebras like Reeh-Schlieder theorem and yeah, von Neumann algebra types, if time permits. But yeah. Okay, so welcome back after the break. Yeah, we have all the definitions, so it's time for examples. So the first sort of obvious example is the Klein-Gordon field, also known as the free scalar field. So I will show you how to construct it using this algebraic framework. So Klein-Gordon, well, we have the field equation like this. So phi is this element of the space of smooth, compactly supported function functions on M. Well, we are going to use something about the properties of the wave operator. So this is the wave operator. Okay, and there are some nice properties of the solution theory for the Klein-Gordon equation. So there exist special green functions for this operator. Let's call this collectively P. So there exist unique, retarded, and advanced green functions. Of P, and we call them E plus and E minus. So what's special about them? Well, green functions, it means essentially the inverse of P. But being retarded and advanced, it means that if we have a test function, so F is a compactly supported guy, and then we apply E plus to it, then the support of that is in the causal future of F, and if we apply E minus, then the support is in the causal past. So this distinguishes those particular green functions. And then with those, we form their difference, which is often called the commutator function for the reason that will become clear soon. So this is the difference between E minus and E plus, and it can be seen as a kind of bilinear form for Fg compactly supported on M, defined as the integral over the whole spacetime, f of x, then E acting on G of x, and this is the standard volume form, which, well, in this case is just D for x. This construction, by the way, also generalizes to curved spacetime. So a lot of these things will also work beyond Minkowski. Although for Minkowski, we can write down the formula for E very easily. So concretely, so E of x, y, well, you can do the whole story with constructing green functions. For the Klein-Gordon operator, you go to the Fourier space and then solve an appropriate equation there. And then you find that your advanced minus retarded object can be written in terms of this Fourier representation as an integral over k sine k x minus y. So this is the Minkowski product over omega, and here notation. So this k underlined, this is a 3 vector, so this is the spatial thing, is a 3 vector. K without underline, this is a 4 vector that consists of omega and k. So this is like a frequency and momentum, and omega is on shell, meaning that we have the solution of this equation. So omega is related to the mass. Oh, sorry, that is, that should be, of course, a k. Okay, so that's something you can verify easily by calculation. And now there's also another interesting property that you might find well, enlightening later on. So there is a sort of behavior of this object E, this commutator function, on a time zero slice on the time zero surface. So in fact, E x y restricted to x0 equals y0 equals 0 vanishes, and its derivative, so example dy0 of E xy, again at the time zero surface, is equal to the Dirac delta on this time zero surface. Okay, so here let's draw a picture. So this is x, this is x0, okay, and well, this is the time zero surface, sorry. The time zero surface is here, so x0, I should write it above, it doesn't really matter, but this is x0 equals 0. And you will see in a minute that these properties here are related to equal time commutation relations. Okay, back to the plot. I was about to construct an example of a star algebra in the setting I introduced. So how do we want to do this? So the simplest way in algebra to specify an algebra is to give the set of generators and relations. So this is what I'm going to do. So here A of M is generated. So this is slightly abstract here because I'm saying, okay, so we have some abstract generators phi of F, where F are smooth compactly supported functions with relations. And these relations are going to correspond to, well, some physical requirements, okay? So as an intuition, this phi of F should be something like a smeared field. So the first natural requirement is that this object is actually linear in F. So this assignment is complex linear. So that makes sense if this is a smeared field. It's Hermitian. So hermiticity. So phi of F star equals phi of F complex conjugate. Now the dynamics, so the fact that we are talking about Klein-Gordon field is implemented as follows. So field equation is that phi of this commutator function acting on F, so that was P, should vanish, okay? And as for, finally, commutation relations. So commutation. Okay, and this should be that the commutator of these two guys is given by I times E of F G times identity. Okay, and that essentially is it. That's how we define well, the quasi-local algebra, and now if we want to assign algebras to regions, so we say that to O, we assign A of O, which is the algebra generated by phi of F, where F is supported in O. Okay, so that was just a dry definition. Now let's try to see some motivation behind it. So first of all, well, this phi of F should be a quantization of like a classical smeared field. So think of phi of F as quantization of a classical functional that just takes your value of the field and then integrates it with some smooth, compactly supported function. Therefore, well, as I said, hermiticity and linearity makes sense. Now the field equation, what would that mean? Well, if I was to take F at smeared with a test function that is in the image of P, so that would be phi of X. Oops. Phi of X PF of X D for X. In this situation, okay, so F is compactly supported. Here we have the integral over Holm-Minkowski. So we can integrate by parts. So we have to do it twice because we have operator second order. We integrate twice. And then we have something which is P phi of X F of X D for X, which vanishes, okay, if phi is a solution. So it's equal 0 if phi is a solution. So coming back to this field equation axiom here, or relation for our algebra, well, this implements the idea that these fields are on shell. So these quantum fields are in some sense solutions to the Klein-Gordon equation. Okay, and finally, the commutator, well, so here I'm going to do something slightly formal. So coming back to this picture above, right? So if we had F and G somewhat, in a neighborhood of the time zero surface, we can imagine taking the limit where they become really flattened. So we have essentially delta in the x0 direction and something that lives only on the time zero surface. So if we restrict this commutation relation to such flattened functions f and g that only live on the Cauchy surface, so only on the time zero surface, then we also have to restrict this e. So these relations here that we have for the commutator function guarantee that from this relation S4, we reconstruct the time zero commutation relations. Which is, of course, just a consistency check that the usual way we quantize the free scalar field works. Okay, so that's the sort of primary example. I can, well, if the time permits, I can tell you a bit about how to quantize interacting scalar fields perturbatively, starting from this picture. But right now, I wanted to say a few words about another concept, which is somewhat restricted to Minkowski spacetime, and yet very important, which is the spectrum condition. So again, coming back to the abstract setting, I want to talk a bit about well, the consequences of the symmetries and the fact that Minkowski spacetime has well, this large Poincare symmetry, and there is something special about translations, and the action of translations allows us to well, distinguish a particular state for QFT on Minkowski that we all know as the vacuum. Okay, so the next small topic is the spectrum condition. All right, I'm just changing this. Okay. So before that, so I already said that there is some covariance property, Poincare covariance of my net of C-star algebras. So this assignment of algebras to regions. So we have alpha of rho is in P0, and that should satisfy the Poincare covariance. So that was back before, that was axiom A4. So this should satisfy A4. But now we want slightly more. So we want this automorphism to be actually implemented by unitary operators, which is a very nice way of implementing an automorphism. So it's an extra property that we can ask. So an automorphism alpha of rho is said to be unitarily implemented if there exist unitaries for each row. So U of rho such that, so in a given representation, pi of alpha rho of A can be written, so this is in a given representation, U of rho, pi of A, U of rho minus 1. So this is unitarily implemented. So if we can do that for our representation, implemented, let's write it explicitly in a given representation. Okay. So if that works for our given representation, then we say that this representation is Poincare covariant. So if this is possible for some pi, then we call it Poincare covariant. Okay, so here is an important fact about the relation between, well, this unitarily implemented automorphisms and GNS representations. So as I told you before the break, one way of getting a representation is to get an algebraic state and use GNS to construct a representation. So now, what if that state has some covariance property? So if a state is invariant under some automorphism, what can we say about this induced GNS representation? Well, ideally, this representation should also be covariant, and this is actually the case. So there is a nice theorem that links a sort of covariance properties of the algebraic state with covariance properties of the representation. So this is, again, a bit more general. So let alpha be just any automorphism of some unital star algebra A, and if a state omega is invariant under alpha, so pulling back, so composing with alpha leaves the state invariant, then alpha is unitarily implementable in the GNS representation of omega by a unitary U in particular, this unitary leaves the distinguished vector of this GNS representation, so the sort of vacuum vector invariant, such that U alpha of omega is the same as omega. Okay, so this is a link between the invariance of a state and unitary implementation in the GNS. So in particular, well, coming back to Minkowski spacetime and Poincaré symmetry, in particular, we can ask ourselves what happens under translations. So what are translations? So translations essentially move us around in space and in time. So now we want to consider a state which is invariant under translation. So it looks the same anywhere in space-time, wherever, anywhere and any time in space-time. So let omega be a state invariant under translations. Okay, so looks the same everywhere. Okay, so the theorem above tells us that we can unitarily implement translations in its GNS representation. So unitarily implemented translations in GNS representation. So let X be a translation. So it's a translation. So to that X, we can associate this operator U of X, which implements it, unitary. And now we assume something about this map from R4 to unitaries on the Hilbert space. So assume this map to be strongly continuous. Okay, so what does it mean? So it's continuous. So it's continuous from R4 to H omega for each fixed. To be so the map X mapping to U of X psi. So this is in R4, this is in H, is continuous from R4 to H omega for each fixed psi in H omega. So that is the strongly continuous assumption. So we have that. If we have that, then we can use Stone's theorem, which is a very powerful theorem, to infer that there are self-adjoint operators that allow us to write this unitary as an exponential of something, which is what we want to do to start with. But these are the mathematical ingredients that lead to that. So Stone's theorem. So it follows that there exist 4 commuting self-adjoint operators P mu. So mu runs from 0 to 3, such that, so what we want to be true is true, so that U of X is simply an exponent, is simply an exponential of I P mu X mu. And we assume here the usual Einstein summation convention. Okay, so these are self-adjoint and commuting. So we can find a projection valued measure that corresponds to this. Oh, I'm probably not saying anything spectacularly surprising that these are components of the four momentum. So we have these components of the four momentum as the commuting self-adjoint operators, and we can find a joint projection valued measure for these things. And the support of that measure will define something known as the spectrum condition. So let me just write this quickly. So there exists a projection valued measure E, sorry, that's again E that I used before, but yeah, okay, there's not enough good letters, such that U of X can now be written as an integral with this projection valued measure. So here, this is written in terms of the eigenvalues, okay? And here the integral goes over the eigenspace. So this is the integral over the space of four momenta. And E is supported inside V plus, which is the forward light cone. So what does it mean? Here is the definition. In momentum space, the forward light cone is all the four momenta such that P mu is greater or equal 0, and P0 is also greater or equal 0. Okay, so again, schematic picture. Here is P sort of spatial momentum. Here is P0, and this is the forward light cone. So, oh, somehow it doesn't want to do that. Okay. Okay, so the spectrum condition here, well, in quantum theory, is related to the, well, physical kind of condition of a positivity of the energy. And, well, so there are like several things coming into that story, right? So we started with a state that is invariant under translations. And as I said, it means that it looks the same everywhere. So you can imagine it sort of, well, intuitively as the state where there is nothing everywhere in space-time. So nothing always looks the same everywhere. So this state has the sort of natural physical interpretation of an empty space. So that's why this corresponds to the vacuum state. This omega, which is translationally invariant, is the vacuum state. And, well, this story here about representation of momenta and so on tells us something about the spectral measure of momentum operator in the vacuum. And that links to the positivity of the energy. Okay, so spectrum condition is something that really makes sense in this form on Minkowski, because we need the translations to act, to be a symmetry of the spacetime. So that doesn't really generalize to curved spacetime, but there is an analog of the spectrum condition also in curved spacetime. So note on curved spacetime, there is an analog and this is called microlocal spectrum condition. So it describes states that are, well, not Minkowski vacuum, because on curved spacetime the notion doesn't make sense, but look like the Minkowski vacuum when studying their singularity structure. Okay, we have still, I think, good 15 minutes. So I want to mention one of the more surprising results about QFT in the algebraic setting, which is the Reeh-Schlieder theorem. So this, again, maybe you have seen it before somewhere. So Reeh-Schlieder theorem. So here, let's take a state that satisfies the spectrum condition above. So let omega satisfy the spectrum condition. And yeah, so this distinguished vector state in the GNS representation is just denoted by capital omega, and let omega be the corresponding distinguished vector in the GNS Hilbert space. Okay. So let's add here another condition that I'm going to add to my list of axioms. So this is A6, which is called weak additivity. Okay. So this is a condition that for any O causally convex pi of A of M. So the representation of this whole quasi-local algebra is contained in the weak closure Okay, I'm going to explain this in a minute. Of the algebra generated by all translations. So by the algebras pi of O plus X, where X runs over all translations. So let's try to imagine it. So we have O, right? We have its corresponding algebra of operators. We can translate it here somewhere, right, by translation X, and we can translate it somewhere else, plus X prime, and so on. And the idea is that this way we can generate all of the quasi-local algebra, all of A of M, just by taking a local algebra of a fixed region, so A of O, and just moving it around and then taking algebra generated by everything. So in a sense, it's not totally crazy to expect that this is the case. But what's interesting is that, well, this is actually enough to prove something much more interesting. So this is the Reeh-Schlieder. So now, again, let O be causally convex and bounded. Bounded region in M. Then, so item 1, vectors of the form A omega, where A is in the representation of the algebra of that region, are dense in H. This is what people usually kind of describe as we can approximate any state in the Hilbert space by just acting on the vacuum vector, on this distinguished vector by local operations. So yeah, imagine again, right, we have this region O, we have A of O, and we are acting in that local region on the vacuum. And that can actually represent any state. So in principle, it can create a state that looks very different from the vacuum somewhere very, very far away on Alpha Centauri. Well, we can approximate that state, but we can approximate it as well as we want. So yeah, by local operations, you can seemingly violate causality because you can create a state which looks very different somewhere else. So this is actually related to the fact that the vacuum state, so this translationally invariant state that satisfies the spectrum condition, that state is maximally entangled. It's very entangled. So the property of being empty space everywhere is very strong. So that has a very strong entanglement. So because of that, if we make some local operations, it's not like super surprising that it can affect things very far away because, well, there is the entanglement. So this has nothing to do with, well, properties of the observables. We have not violated causality for the observables, but effects like that are actually encoded in the states and the entanglement property of the states. So that's the first statement in the Reeh-Schlieder theorem, and the second is maybe less spectacular. So if A is in pi of A of O, and it annihilates the vacuum, so satisfies A omega equals 0, then it means that A equals 0. So these two properties, so the first one is called, well, says that omega is cyclic. So this means that omega is cyclic for every local algebra. And this means that omega is separating. And in fact, these two properties of having a vector which is both cyclic and separating for every local algebra in a given representation, this is important for something called Tomita-Takesaki theory. So the existence, so this is the modular theory of a cyclic and separating vector is the starting point of Tomita-Takesaki theory, also known as modular theory. Okay, and this is very useful. I mean, that yeah, construction and properties of modular operators, they are a very useful gadget. Sorry, do I have 8 more minutes, or should I finish before and leave time for questions? What's the...
No, it's okay. You can finish. No
Okay.
worries.
In this case, well, the last topic I wanted to briefly cover is, well, how do we get from this story, which, you know, for now it was just in terms of star algebras and C-star algebras. So how do we get to von Neumann algebras? And well, this Tomita-Takesaki theory actually is something that happens in von Neumann algebras. So how do we define von Neumann algebras of regions? Okay, so here, well, I was very general. I was very general up to now, and things worked in general star algebras. But now let's well, restrict ourselves to the C-star algebra case. So consider a net of now C-star algebras. Okay, so O goes to A of O, and we want these to satisfy axioms A1 to A5. A1 to A5, so not necessarily the weak additivity. So take a state omega, then take its GNS representation, take GNS rep of omega. So now for any region O, bounded causally convex as usual. So for any region, we can define an algebra by the following. So let's take the representation of this A of O in the GNS representation of omega. And now let's take a double commutant. So the commutant of an algebra, of a subalgebra of operators in a Hilbert space is all the operators that commute with that. And then let's take it again. So this object is, well, let's call it M omega of O, double commutant. And this is a von Neumann algebra. A von Neumann algebra. This is a concrete von Neumann algebra in, well, obtained as a double commutant inside a fixed Hilbert space. One can talk about abstract von Neumann algebras, W star algebras, but that is maybe, well, not necessary to understand what's going on in QFT. So yeah, just for completeness, let me write down the definition of the commutant. So B, so that B be a subalgebra of all bounded operators in a Hilbert space. Okay, then B prime, the commutant is all A in B of H, such that A with B commutator is 0 for all B in B. Okay, so that's a commutant, and the double commutant is, well, you do this twice. So taking this double commutant is some kind of closure. So this is a certain closure or completion of pi omega of A of O. So given your local observables in the C-star algebra, you can take this double commutant and you get more. So it's a certain closure. Yeah, you can think of the elements, because it's a closure, you can think of the elements of this commutant as limits of observables localized in that region, and the commutant would be the limit of observables localized in the causal complement of that region. Okay, so maybe let me just explain that point. So we know, so if we have a region O, right, we know from Einstein causality that everything which is localized in the causal complement of O, all the operators localized in O prime would commute with O. So A of O prime and the representation is contained in the commutant of O. So using the prime for both things is actually not a coincidence. So yeah, so observables localized in causal complement are inside the commutant. Yeah, so somehow we can think about the elements of this von Neumann algebra as some sort of limits of things localized in O prime. And well, it's kind of reasonable to expect that these do not intersect with limits of things that are localized in O, because then we would have elements that can be thought of both sort of localized in O and in the causal complement. So it's reasonable to assume that the intersection of M of O and its commutant is trivial. So it's just multiples of identity. And if that's the case, then we say that M omega of O is a factor. So factors are actually kind of, well, physically reasonable completions of local C-star algebras. Okay. So then a thing that one does in algebraic quantum field theory, well, we can actually use some mathematical classifications of von Neumann algebras. So there's the whole story about various types of von Neumann factors. There has been a lot of excitement about it recently. So generically, local algebras are type 3, but there are some other observables which are non-local, which belong to this quasi-local algebra that are type 2. And well, that's the whole different story that I will tell you on another occasion. But for now, thank you very much for your attention. And yeah, thank you very much.